Okay, for example, this is a variable capacitor. It's a capacitor whose capacitance can be changed by this. Here you have a tuning knob usually. I mean, this you can see in old radios. If you have ever seen an old radio, there's always this knob which you rotate. If you open the radio, you will see that it is connected to this knob over here of a variable capacitor. So how this works is, if you see over here, you have these plates. These are movable plates. These are fixed plates. By rotating this one, you are basically changing the area where these fixed plates and the movable plates are overlapping. So if in this case there is a little overlap, if you rotate it a bit such that this plate overlaps completely with this one, you will have a larger area for the capacitors. Well, you can think of this as, in fact, many capacitors connected in parallel. These are not series, these are parallelly connected. So here you are changing the capacitance of a capacitor by changing the area. Now the question is basically asking what happens, how do you change the capacitance by changing the D? Well, there are various ways you can look at this problem. Since by changing D you are not changing the electric field inside the capacitor, if you reduce the D, that means you are lowering the potential. If you increase the D, you are increasing the potential. Or you can look at the same problem if you remember the definition of the capacitance. The capacitance was epsilon 0 A over D. So if D is decreasing, C is increasing, and remember V is equal to Q over C. So if C is increasing, V is decreasing. Well, you can do a similar thing for area. If area is increasing, well, if area is increasing, you can just use the analogy with the parallel plate capacitor. If you are increasing the area, the charge will be distributed in a larger area. If the charge is distributed at a larger area, electric field is being reduced, so the potential should be reduced. Or let's say if area is being decreased, the charge density is increasing, capacitance is decreasing, the charge density is increasing. If the charge density is increasing, you are increasing the electric field. Since you are increasing the electric field over the same distance, then V is increasing. So for example, what you can do is you can just take a capacitor that has a large surface area and charge it through some potential using a battery. And then what you do is you lower the area by, for example, using a variable capacitor. You reduce the capacitance, but this would cause an increase in the potential across your capacitor. So if you, for example, reduce the area or reduce the capacitance by a factor 10, you are basically multiplying your voltage by a factor 10. Okay. If we decrease the distance. Now you see, in a parallel plate capacitor, if you don't change anything else other than the distance between the plates, so in that case you are keeping the electric field fixed. So if the electric field is fixed, remember V is equal to E times D. If electric field is fixed, so the voltage is proportional to the distance. Other questions? Okay, now let's discuss what happens with the dielectrics. Now this time what we will again stick with the example of a parallel plate capacitor. So we have a plate over here, and we have another plate somewhere over here. The plates have an area A, their separation is, let's say, D, and we fill in between by some insulator. Like you take a plastic, you put a plastic inside, and you fill it by your insulator. You are not heating it. You are just charging it. It's an insulator. Now the question is, what is the capacitance of this system? Remember, if we didn't have this insulator, let's go, without insulator, capacitance was equal to epsilon 0 A over D. This is what would happen if we didn't have any insulator in between. Now we have the insulator in between, what happens to the capacitance? We need to calculate the capacitance of this system. And remember, whatever system you want to calculate the capacitance of, the only thing you have to do is just carry some charge from one conductor to the other one and calculate the potential difference. That is what we still need to do. So we put some positive charge over here and some negative charge over here. So what would be the corresponding electric field in the space in between these two conductors? 0. Why? Now, if the insulator was a conductor, then we know that in the conductor we cannot have any electric field. So inside the insulator we will have 0 electric field. So the only electric field will be non-zero in places between the plates and the conductor, if they're in such space over there. Only in those places we will have some electric field, which will create some capacitance. But this is not a conductor, this is an insulator. In an insulator, inside an insulator, there is no reason why we shouldn't have any electric field. What do you mean by electric permeability? So, I mean, okay, so if you don't know it, don't use something you don't know. I mean, how can you explain this using the things that you already know? No. Sigma over epsilon 0. Okay, your friend says that the insulator will have absolutely no effect. No, I mean, I know something about the insulators though. For example, plastic, I know something about the plastic. I know that the plastic is made up of atoms. And I know that in a conductor, I know that at least in a metal, I know that the electrons are free to move. In a conductor, the charges are free to move. In an insulator, in a dielectric, there are charges over there, but they are not allowed to move. An electron cannot just move 5 meters in an insulator. There will be some polarization, which basically means, let's look at the atom. What's an atom? Atom will be, we have this positively charged nucleus over here. Around it we have these electrons. Now, if we put this in an electric field, I mean, you can do the same argument for a molecule. Or you can even do this for a dipole. Now, let's discuss the dipoles later on. Let's just take an atom. We have an electric field. Now, the atom is very small, so in the volume that the atom occupies, the electric field will be more or less constant. So we have these nuclei, which is positively charged, and around it we have the electrons, which form a cloud. So we have the electric field, and we put the atom inside. Now, if it might be that this atom doesn't have any polarity, the negative charges are homogeneously distributed, the center of the negative charge and the positive charges are the same. But the moment that we put it in an electric field, the positive charge will be pushed in one direction, the negative charge will be pushed in another direction. So if we just put this atom in an electric field, what will happen is that the positive charge will move in one direction, whereas the negative charge will move in the other direction. So there will be some displacement. And it will be effectively, you will have what's called, the atom will be kind of elongated. On one end, you will have negative charges. On the other hand, you will have positive charges. So that's what will happen when you put an electron inside an electric field. Now the insulator is just made up of atoms, neutral atoms or neutral molecules. And we are putting all of these atoms in an external electric field. Remember, initially we have these plus charges and negative charges. They will create an electric field given in this direction, E0. This E0, its magnitude will be sigma over epsilon 0. This is the electric field in the absence of insulator. So we have this initial electric field. We put a dielectric inside, an insulator inside, which is made up of neutral atoms. There are no free charges moving around. But nevertheless, the positive charges will be shifted slightly in the direction of the electric field, and the negative charges will be shifted slightly in the opposite direction. Now, there's an electric force due to the nucleus, which is holding the electron in its place. No, we are not winning over it. The electron is still there. Well, it's not that difficult to start with, but because the electrons are feeling only the electromagnetic force. It's not feeling nuclear forces. But we are not winning over this force, but nevertheless, initially, due to the presence of the electric field of the nucleus only, we have some homogeneous distribution of negative charges. Then we are putting this external influence. It will modify the negative charge distribution slightly, very small amount. Well, in some material it might get even larger. In some materials it will be very small, by some amount. That's the only point we are making. I'm not saying that this slight negative charge is equal to the charge of one full electron. It will be very small. So initially we have these parallel plates. Inside there is this insulator. Now we have all these dipoles inside. So this was positively charged. This was negatively charged. Now inside, this end of the dipole is slightly negatively charged. This is slightly positively charged. This is slightly negative. This is slightly positive. This is slightly negative. This is slightly positive, slightly negative, positive, negative, positive, etc. And for all the dipoles, I mean, the whole thing will, you can just think of the whole insulator as a collection of dipoles which will be oriented in this form. Now, you see, if you look at this point, somewhere over this point, I have a positive charge and negative charge more or less at the same point. So they will cancel each other. So the positive charge of this dipole and the negative charge of this dipole will cancel around here. And the positive charge of this dipole at this end and the negative charge of this dipole at the other end will also cancel each other. So inside, I won't really get any charges. Nowhere, I won't see any charges on the inside of this insulator. So this system will look like this one. Oops, sorry. And here I have my insulator. Inside there are no charges because the positive and negatives from different dipoles, they will cancel each other more or less. But if you look at on the surface, all the dipoles close to the surface have a negative charge towards the positive plate, which are not cancelled by any charges. So these negative charges will remain there. And similarly, on the other surface of the insulator, I have these positive charges, which are not cancelled by any dipole. The positive ends of the dipoles on the surface they are not cancelled by anything else. The negative sides of these dipoles on the surface are cancelled by the positive sides of other dipoles inside the insulator, but that doesn't hold for the dipoles outside. So the other surface will look like as if it is positively charged. Now, in the case of a conductor, these are actual free charges that move from one part of the conductor to the surface. But in an insulator, they are not really charges that move from some other part. They are actually the charges right at that point, slightly displaced. You can just think of it, I mean, this is one way of looking at the charges. Or you can say that if you have any material, it's a collection of positive charges and negative charges uniformly distributed. If you put this in an external field, the negative charges will be slightly shifted towards the positive plate, and the positive charges will be slightly shifted to the negative plate. So on the surfaces, you will still get some effective charges. Although they are not free to move, nevertheless, the surfaces will behave as if they are charged. So let's look at inside. Now we have this original electric field. Let's say this is our z-axis. Now the original electric field was sigma 0 divided by epsilon 0 in the z direction. This was the original electric field. Now we have a second electric field created by these induced charges, by these negative and positive charges in the insulator. They are induced by the external electric field. Now we can model them very simply by sigma induced divided by epsilon 0, but this time they are in the minus z direction. So this sigma induced is the effective surface charge of this dielectric. Now the total electric field which is E0 plus this E induced. This is sigma 0 minus sigma induced divided by epsilon 0 in the z direction. Now, what is the sigma induced? We don't know. It's a property of the material. For some materials, it will be quite easy to displace the electrons relative to the nuclei because the forces between at least one electron and the nuclei will be weak. In some other materials, it will be really hard to separate them. And depending on the properties of this material, the sigma induced and hence the total electric field created inside an insulator in response to an external electric field will be different. Well, one thing we know, this electric field, now let's see, we said that this is sigma 0 minus sigma induced divided by epsilon 0 in the z hat direction. It will be definitely less than E0. The electric field inside my insulator will be smaller. It will not be as small as as a conductor. In a conductor, it will be completely 0. But in an insulator, it will be the electric field inside the insulator will nevertheless be reduced in strength. But this means the potential difference will be less than the potential difference in the presence of the insulator will be less than the potential difference in the absence of the insulator for the same Q, for the same charge. And remember, V is equal to Q over C. So this means that the capacitance increases if we put an insulator. This is the capacitance in the absence of insulator. This is the capacitance in the presence of the insulator. Now, what is this E? What is the total electric field? For a general material, of course, we don't know. And we have to know some more properties of the material. But we at least know that it is a function of E0, the electric field that we apply. Because if we don't apply an electric field to the insulator, there won't be any electric field inside the insulator. If we start applying an electric field in the insulator in one direction, well, then we will probably, in most cases, we will get an electric field in the insulator in the same direction. So this basically tells me that the total electric field is a function of the applied electric field. It will have some, let's say, some constant times E0 plus maybe some other terms in the expansion. This, of course, this is an assumption. This is what is called a linear dielectric. This much term. In a linear dielectric, we have the total electric field inside is proportional to the applied electric field. We also have nonlinear dielectrics, but within this course, at least, we will be restricting our attention to the linear ones. So we know the electric, well, this one, well, E0, we already know that E0 is sigma over epsilon 0. And this epsilon 0 over K that we define as a new parameter, which is we call the electric permeability. How much electric field does this dielectric allow to be built inside it? Now you can imagine a conductor to be a dielectric with an infinite permeability. It doesn't allow anything inside. So the electric field inside the capacitor with the insulator is now sigma over epsilon. So everything else is the same as if there is no, the only difference that the insulator causes is the modification of this parameter epsilon 0 to epsilon. And this tells us that the capacitance will be epsilon A over D. Which is kappa times C0. This is the effect of the dielectric. What is the permeability? Well, in a sense, it is kappa epsilon. Well, I think this coefficient is not defined as kappa, but 1 over kappa. But nevertheless, within these definitions, this is what the electric permeability is. Sure. I mean, you have the average over the dipole moment. I mean, you see, if you have a dipole, I mean, here I just assume that the atoms doesn't have their dipole. But in practice, when you look at the molecules like the carbon dioxide, most of the molecules, they have their own polarity. They are dipoles. They are not neutral atoms. So if you take a dipole and put it in an electric field, what happens is that the dipole also tries to rotate. But eventually, the configuration will be like this. The minus sides of this dipole will try to align, try to go towards the positive plate, and the positive sides of the dipoles will try to go to the negative plate. Now, how much do they align? You can, of course, relate this kappa within a model, of course, to the dipole moments that you are either create or that's already there. I mean, that you will do probably in your third and fourth year. Here they are connected. They do touch each other. There is no empty space over here. I just plot the empty space to denote, to emphasize that they are different materials. Well, you see, you will be creating a current from the positive plate to the negative plate, and hence your capacitor will be short-circuited. Now, the thing that we did is we had seen that after all this discussion, the effect of the insulator is just to modify this coefficient epsilon 0. Well, air itself is a dielectric. Yes. In fact, this epsilon 0 in vacuum and in air, I mean, if you build a capacitor here, you will not use the epsilon 0 in vacuum. You will use the epsilon of the air. We are not yet using this electricity. Now, suppose you want to have a capacitor with a really large capacitance. Maybe you need it. Then you can use a dielectric. I mean, a really large capacitance, by the way, the unit of capacitance which we didn't discuss is farad. If you try to build a capacitor with a capacitance of 1 farad that is separated by 1 millimeter, it turns out to be of the order of meter squares, the area you need. That's a huge. You cannot build it. But if you use an insulator that has a large dielectric constant, large epsilon, then you can build a tiny one. Now, we didn't yet discuss what do you use capacitors for. And that's another story. But here, if you need a capacitor that has a large capacitance, well, one thing is if you need a capacitor with a large capacitance, using insulators or using dielectrics is inevitable. They increase the capacitance so you can store more charge there. Another thing is if you want to build a parallel plate capacitor with a very small d, well, you cannot just hold two large plates at a separation of 1 micron, for example. You have to put some material in between so that they do not short circuit. Now, if you use a conductor in between, that means it has zero capacitance. You cannot store electric charge there. Remember, we are in capacitors. The main purpose of the capacitors is to store charge. If you put a conductor in between the plates, you are not storing any charge. No, we are storing charge. We want to store charge. But of course, if you build a huge electric field, you cannot store charge. If you put a conductor, of course the electric field goes to zero, but the charge, it goes to zero because charge disappears. No. No, I mean, if so you are saying this one. So you just put some and you're okay, so example. This is your friend's question. So let's take two parallel plates, put some metal in between, conductor in between. And then insulators here, so that the conductor doesn't touch. Yes, these are our insulators. Sure. This is equal to this one plus this one. So let's see, this is in fact C1, C2 connected in series. So we know the equivalent capacitance of this system is less than C1 or 2. You cannot store charge here. You store less charge here for a given potential. So if you put conductors in between the plates, you are reducing the capacitance. Because they flow from the positive to the negative plate. Now let's do an example. Where we have a conductor, an insulator, only halfway. No. In fact, these are parallel connected two capacitors. I mean, if you connect these two areas by a conductor, you are effectively making sure that these two areas are connected to each other. I mean, whether they are actually connected like this or through a conductor doesn't make any difference. That's basically what we are using here. Now, another thing that, I mean, this way, you just have two capacitors. You can calculate the capacitance of each one of them separately and then connect them connected in series. But you can also look at this problem directly. So what is the, I mean, the first, if you put the capacitor over here, the insulator over here, I mean, suppose you ignore the insulator first, there's no insulator, then you have some charge distribution. Putting this insulator over here changes the charge distribution on the plates. That is what you should pay attention to. So when you put the insulator, let's say that we have a charge, here we have, let's say, sigma 1. In this region we have sigma 2. Here, of course, we will have a charge density minus sigma 1. Here we will have a charge density sigma 2. Now, the thing you have to pay attention to in order to determine these sigma 1 and sigma 2 is that the potential difference between these two plates have to be the same, whether you calculate them along this line or you calculate them along that line. So you see here the electric field, let's say its magnitude, will be sigma 1 over epsilon. Here, when there is no dielectric, the electric field will be sigma 2 over epsilon 0. If this is the point A, this is the point B, the potential difference between A and B is E1 times T, or it is E2 times T. So these two electric fields have to be the same. If these two electric fields are the same, sigma 1 over epsilon 0, epsilon should be equal to sigma 2 over epsilon 0. And we also know that Q, let's say this is area 1, this has a total area A1, this has a total area A2. Q is equal to sigma 1 times A1 plus sigma 2 times A2. We know the total charge, so we can actually solve for sigma. We have two equations that relate sigma 1 and sigma 2. You can solve for sigma 1 and sigma 2 using these two equations. Once you know sigma 1 and sigma 2 in terms of the total charge, you know the electric field in terms of the total charge. Once you know the electric field in terms of the total charge, you know the relation between the potential difference between these two plates and the total charge on these plates. And that proportionality constant will be just your capacitance. It gives you exactly this result. Questions? An exercise for you. You see, the thing is, you have to solve for the whatever the configuration of your conductors are. You have to find the corresponding electric field. If you have a complicated shape, the electric field will be complicated to calculate. Because in a conductor, okay, the charge itself doesn't determine the electric field only. Because the electric field has to be perpendicular to the surfaces. So the charge redistribute themselves inside the conductor to make sure that there's the electric field on the surface of the conductor is perpendicular. So you don't know the charge distribution. You don't know the electric field. You have to solve for both of them at the same time. It will be a complicated problem. This, oops, sorry. This question. So we have the battery. We have 3 identical capacitors. They all have the same capacitances. We connect them to a battery and they are charged. Once they are charged, the battery is disconnected. You just remove the battery. After you remove the battery, well, what happens to the charges? Before you remove the battery, what happens to the charges? After you remove the battery, what happens to the charges? So are all the charges in all these capacitors the same? Which one is larger than which other one before you remove them and after you remove them? If you think you have found the answer, ask your neighbor to make sure that they have the same answer. I only remove the battery. I don't change any other wiring. Okay, let's take the votes. How many of you think it is 1? How many of you think it is 2? 3? 4? So 4, I see some hands. A is larger than B, which is equal to C, and after you remove the battery, there won't be any change. 5. So you say that A is larger than B equal to C. After you remove, they will all be equal. 6. 7. Okay, this is homework for you. We will discuss this on Tuesday. I would vote for 4.